Welcome back, everyone. In this video, we're going to learn about real gases. Up until this point, we've talked about ideal gases and the ideal gas law. But it turns out that not all gases behave in an ideal manner. In this video, we're going to discuss why this is the case and what happens. So when we look at the molar volume of a gas, for ideal gases, we calculated this to be 22.414 liters at standard temperature and pressure. When you look at the molar volume of actual gases, then you can see that it fluctuates somewhat. What gives rise to these variations? Well, the kinetic molecular theory describes ideal gases, and we talked about the 5 key postulates of the kinetic molecular theory. However, as pressure increases and as temperature decreases, then 2 of those key assumptions or postulates break down. Postulate number 2 states that molecules are small and that the volume that the molecules occupy, or the volume of the molecules themselves, is much smaller than the volume of the actual container. However, molecules do have a measurable size, and we'll see that there are certain conditions that we can put the molecules in that exacerbate that issue and that make the size of the molecules have an important factor. The third point, the third assumption, is that molecules do not attract or repel each other, that there's no intermolecular forces. But we know that all molecules actually do have intermolecular forces. And so there are conditions under which these interactions play a role, and there are conditions under which they don't. So when the intermolecular forces don't play a role, when the molecules' actual sizes don't matter, the gases behave ideally. However, when the molar mass or the size of the molecules does matter, and when they do exert intermolecular forces that play an important role, then these deviate from ideal behavior, and we call those real gases. So let's evaluate the conditions under which these occur. So at high pressures, the second postulate of kinetic molecular theory does not hold true. At high pressures, what we're doing is we're shrinking the size of our container. And when we do that, the molecules are taking up a larger proportion of the available space than if there's a large volume. What happens in that case then is that the volume of the container is not much larger than the volume of the molecules. This leads to having non-ideal behavior. This is a plot that looks at pressure times volume over moles and temperature as a function of pressure. Or in other words, that's the ideal gas law on the left as a function of pressure. What we see is that at low pressures, at pressures of approximately atmospheric pressure and thereabouts, that there's not any real deviation. However, if you increase the pressure up to 25, 50, 100, 200, 400 atmospheres of pressure, then we see actually that all gases tend to behave less like ideal gases, and the size of the molecules is now playing a factor. So again, for an ideal gas, we would expect there to be no deviation. There is unity when it comes to the relationship between pressure, volume, moles, and temperature. However, for a real gas, there is deviation. And this is due to, in part, the molecules themselves taking up space. Another factor which causes gases to behave non-ideally is having low temperatures in addition to high pressures. And under those conditions, the third postulate is not true. And molecules in those conditions do exert attractive intermolecular forces. What we can see here is the function of ideal gas behavior as a function of both pressure and temperature. So what we see is that for all cases, at very high pressures, there's deviation. However, at high pressures and low temperatures, there's even more deviation than if the temperature were higher. And so as the pressure increases, what we see is that the molecules are closer together on average. That's because our volume is shrinking. Because the molecules are closer and because the temperature is decreasing, they're interacting with each other. And so at lower temperatures, the root mean square speed of those gases goes down. And therefore, they don't have as much kinetic energy to overcome the attractive interactions between the gas molecules. Thus, we see that these gases are going to deviate from the ideal gas law. And they will based upon the strength of the intermolecular forces. Under the same set of conditions, so for the same temperature and same pressure, molecules that we could identify as having strong intermolecular forces, so molecules that might interact through hydrogen bonding or be polar or have very strong London dispersion forces because of large molar mass, these molecules will deviate the most from ideal behaviors. All right, let's try a problem here. Under which set of conditions would the ideal gas law be most accurate in describing the behavior of a gas? Pause the video and think through this on your own. Welcome back. So how do we think about this? Well, we know that deviation from ideal behaviors happens at low temperatures and high pressures. And the reason for that is because they have lower kinetic energies and because they're being pushed together into close quarters. Therefore, because they have strong intermolecular forces, or rather gases that have strong intermolecular forces and are under those conditions are going to behave very much like a non-ideal gas. And so if we want gases to behave in an ideal manner, then we need to have very, very high temperatures and very, very low pressures. So the answer there would be A. That's it for this video. Thanks for watching. Have a great day.